Good afternoon, everyone. Today we have a pleasure to attend the talk by Professor Bruno Lourenço from Institute for Statistical Mathematics. Professor Bruno Lourenço made his bachelor's and master's degrees at University of Brasilia in Brazil, and then made PhD at Tokyo Institute of Technology, and after that held several academic positions in Japanese universities, and now he's professor at Institute for Statistical Mathematics. I guess I'm repeating myself. Okay, so please welcome Professor Lourenço.
Thank you very much for the introduction, and also thank you for the opportunity to present at this seminar. So today I'm going to talk about oddities in the pursuit of self-duality. So this is based on joint work with several colleagues of mine, João Gouveia in Coimbra, Masaru Ito in Nihon University, in Lin, Hong Kong Polytechnic University, Scott Lindstrom at Curtin in Australia, and T.K. Pong at the Hong Kong Polytechnic University. So just to start, let us just recall some definitions of the basic objects that will appear through this talk. So we'll be mainly interested in convex cone. So a convex cone containing some Euclidean subspace is just a set that is closed by positive linear combinations. So whenever you pick two elements in K and two non-negative alpha and beta, alpha x plus beta y are in K. Closed under non-negative linear combinations. And in particular, we have that a K is a polyhedral cone if you can express K as the set of solutions of finitely many inequalities. So this is the same as saying that there exists some A such that K can be written, there is some matrix such that K coincides with the set of solutions of AX greater or equal than 0, where this greater or equal is understood as being component-wise inequality. And if we are in some Euclidean subspace, we can assume that we have some inner product and define the corresponding dual cone, which is just the set of y's that make non-negative inner product with each element of the cone. Now, let us see some examples. For example, if we have the non-negative orthant, so the set of elements for which each component is non-negative, its dual under the usual Euclidean inner product is just the cone itself. And if I consider the cone of n by n positive symmetric positive semidefinite matrices, and I consider the usual Frobenius inner product, then this cone is also, its dual also coincides with itself. Now, a slightly less trivial example might be when you consider the p-cones. So what is a p-cone? So I consider the p-norm, and here p can be anything between 1 and infinity, including the possibility of being the one norm of the infinity norm. And I consider the set of elements such that T is greater than the P norm of X. Now, if I consider the usual Euclidean inner product, the dual of the P cone will be the Q cone, where 1 over P plus 1 over Q is equal to 1. And a particular case of the P cone is when you take P equal 2. So this gives rise to the famous second order cones, also called ice cream cones. And now the research question I was trying to address throughout some of the works is to understand how common self-dual cones are and how to identify a self-dual cone. Now, there are some disclaimers that I must make. So here I'm considering self-duality in a general sense. So I'm saying that a cone is self-dual if there exists some inner product under which the cone coincides with its dual. Now, please notice that if you fix one inner product, it's not typically hard to verify that under this specific inner product, your cone, say, is not self-dual or is self-dual. So for example, under the Euclidean inner product, it's not very complicated to verify that the P cone is different than the Q cone. What is harder is to verify that the P cone and the Q cone are never the same, no matter which inner product you select. So it's in this sense that we want to examine, for example, where the P cones are self-dual. So not with respect to one fixed inner product, but it's an existential question. If there exists some inner product that makes things self-dual. Now, a reasonable question will be, why do we care about the choice of the inner product? Well, at least from my point of view, one reason why I care about these things is that there is a class of cones that have very nice properties. They are called the symmetric cones. And I'm not going to go into the detail what it means to be homogeneous, but in any case, we say that a cone is symmetric if it's homogeneous and self-dual. And if it turns out that the cone is symmetric, you can attach a very powerful algebraic object called an Euclidean Jordan algebra. Now, what's important is that the self-duality requirement for this theory to work can be met by arbitrary inner product. So that's why, that's at least this is one of the reasons why it's important to study self-duality in this more general sense. So I guess at this moment, maybe I should stop and ask, are there any questions about our setting? If not, let me continue a bit more. So formally, I'm just stating things formally. So the self-duality problem is, given a certain K, can we find some inner product such that the cone coincides with its dual? Now, one thing is that the dual changes as you change the inner product, but it cannot change in a too crazy fashion. There are some restrictions in the way that the possible duals are related. So one thing that happens is this. So for example, if you fix one inner product, say the Euclidean inner product, all the possible inner products, all the possible dual cones, they are isomorphic to that original fixed dual under a positive definite matrix. So the question of whether we can find an inner product that makes this cone self-dual can be simplified a bit. It's enough to consider the dual cones, say with respect to Euclidean inner product, and then it's possible to show that K is going to be self-dual if and only if you can find a positive definite matrix that maps the cone onto this fixed dual. And now you can get a bit more of sense of why this question is more complicated than this. Because in order to check that, for example, a cone is not self-dual, it is essentially an isomorphism problem. You have to show that a cone is not isomorphic to its Euclidean dual. And it can still be isomorphic, but it cannot be isomorphic through a positive definite symmetric matrix. So there are some connections with the self-duality problem and the so-called isomorphism problem. So the isomorphism problem is the question of, given two cones, two closed convex cones, K1 and K2, is the question of whether I can find a linear bijection that maps one cone to the other. So the self-duality problem can be understood under this light. So to say that K is not self-dual is the same thing as saying that K and its Euclidean dual are not isomorphic through a positive definite matrix. And are there any questions so far? Yes. Yes, so for example, later we'll take a look at the case of polyhedral cones. So for polyhedral cones, you can assume, for example, that the cones are given by a set of linear inequalities. It will depend a bit on the family of cones that you are discussing. Sometimes you are going to be given a concrete expression, right? And then in this case, it can be transformed into an algorithmic question. But it depends a bit on the specific cones you're looking into. I'm not sure, does this answer your question?
I think it's good.
Okay. Yes. Now, some years ago, we took a look into this question for the specific case of the p-cones. And we found out the following. So if you pick a p and a p hat, strictly between 1 and infinity, what you can show is that p and the p cone and the p hat cone, if p hat is different than p, they are never isomorphic. You can never find a linear bijection that maps one cone to the other. And we also found something about what's called the automorphism group, so the set of matrices that map the cone to itself. If p is different than 2, then the automorphisms of the p cone coincide with the, not coincide, but if this holds, then it must be an automorphism of the one cone. And in particular, so this first item here will imply that if p is different than 2, then this can never be self-dual. And with a bit of more work, you can show that it's not homogeneous as well. But there is one exception, which is the case of the one cone and the infinity cone. In 3 dimensions, they are in fact isomorphic. So what happens is that if you pick the one ball, if you pick the one ball in 2 dimensions and the infinity ball in 3 dimensions, they look like this. So you can map the one cone and the infinity cone, they are just lifting these objects to a higher dimension and then conify things. So they are essentially rotated versions of one another and stretching things a bit. However, it's possible to show that they are isomorphic, but never through a positive definite matrix. So these cones are not self-dual neither. Are there any questions?
The difference between isomorphism and isomorphisms to a positive semidefinite matrix geometrically is that you cannot rotate basically, right? You can only kind of squish them.
Yeah, so you cannot rotate, then you get outside of it. Now, the techniques we used to prove this were a bit ad hoc and were very specific to the case of the p-cones. So essentially, it boils down that if you pick a p-cone and you remove the vertex, if you remove the origin, the boundary of the p-cone is an embedded manifold. And depending on the value of p, this embedded manifold will have different degree of differentiability. And this will constrain the kind of linear maps that you can have from one p-cone to the other. So after carefully analyzing this, you can get this kind of conclusion. So this statement was already included in this paper now almost 5 years ago. But recently, together with Scott and Tim Kay, we revisited this question in the context of understanding the error bounds of p-cones. So I'm going to make a brief detour to explain what is our more recent technique to understand this kind of questions. So a few years ago, together with Tim Kay and Scott, we defined some object that we called one-step facial residual function. So this is a bit technical, but the idea is this. You pick K, a closed convex cone, and you pick Z, an element in the dual cone. So because Z is an element of the dual cone, the Z will determine some half space, and this half space is going to expose some face of K. Now, what is a one-step facial residual function? It's a function that is essentially giving an error bound for this question here. So the question is this. If I'm close to the cone and I'm close to the half space determined by Z, I want to understand how close am I to this intersection. And the facial residual function will give an upper bound to this quantity. So this is essentially an error bound question. I have two sets that intersect. If I'm close to both sets, I want to understand how this reflects onto the distance to the intersection. So put otherwise, I want to upper bound the distance to the intersection of two sets by something that resembles the individual distance to these sets. And the motivation for defining this stuff was to get, there's a type here, used to compute error bounds for conic linear programs. Now, what we did in this more recent paper was to observe that if you have isomorphic cones, they must have the same kinds of error bounds. So again, this creates a constraint on the way that you can map one cone to the other. And this also creates a constraint on the way that a map can map a cone to itself. And we use this idea to rederive this result in a slightly more elementary way. And more recently, we also did this to study some algebraic properties of an object called power cones. So I'm just trying to give a bit of intuition on how, for example, this kind of question can be proven. So that will be the end of the initial part of my talk. So maybe I would like to stop a bit and ask if there are any questions so far.
Does it make sense to ask about an indefinite inner product? And then you don't need a positive definite matrix?
Yeah. I mean, what you mean? Well, what would be the question in this case?
You define polarity with indefinite inner product.
Okay.
And then you would have some polar with respect to indefinite.
Okay, I see. And then you would have a cone, and then you could try to ask whether it's isomorphic to something. Yeah, I haven't thought about this, but this is also an interesting possibility. Yeah, thank you for the question. Now, working on these questions for general cones, we got a bit the feeling that they are hard for general cones. So I teamed up with João to try to look at a slightly easier class of cones, which are the polyhedral cones. And so the question we were trying to address now with this work with João was how to identify self-duality for polyhedral cones. Now, for polyhedral cones, there is a very powerful technique, and that's I like very much. But João is the actual expert on these things, called slack matrices. And through slack matrices, we were able to get 3 results. So one result is sort of expected. One result, I think it's a bit surprising. And the last one is a bit weird. So I'll mention them in order. But first, I need to talk a bit about slack matrices. So what is a slack matrix? I have K, a polyhedral cone. And because I'm polyhedral, I have finitely many extreme rays at the primal cone and also at the dual cone. So I can enumerate them, and then I can build the matrix that corresponds to the inner products between extreme rays of primal and extreme rays of the dual cone. And why would one do this? Is because you want to encode the properties of K in matrix format. And there is something very nice that happens, is that studying a specific slack matrix of a cone reveals lots of properties of this cone. And you can use the tools of linear algebra to study the structure of K. So as far as I know, the first work that considered this kind of approach was a work by Yananakis in 1991. And João, and together with his co-authors, they've done recently many works studying the properties of these slack matrices. Now, just to make things clear, let's see one example. So for example, if I pick the 3-dimensional non-negative orthant, the extreme rays, they are generated by the unit vectors, and this is self-dual. So these are possible slack matrices. For example, I can pick the identity matrix. I can also pick this matrix. It depends on the way that you order the extreme rays of the primal and the dual. Now, here's another example. I can pick, for example, the L1 cone in R3. So this is the cone generated by the one unit ball in the 2D space. So you pick the one unit ball in the 2D space, you lift it, and you construct a cone. So, for example, this is one example of slack matrix. So I enumerate the extreme rays, and I get this. Now, here is a slightly more interesting example. I can pick a regular pentagon on R2, so like this. And again, I do the same thing. I put this one dimension higher, and I conify this. Now, this cone is self-dual, and the extreme rays of both the primal and the dual will look like this, and this will be an example of a slack matrix. So the first result we obtain is one thing that I think is more or less expected. I'm not sure if I'm talking now with the benefit of insight, but yeah, so what it turns out that in order for a polyhedral cone to be self-dual, it is enough to find one slack matrix that is positive semidefinite. So I guess it seemed more or less expected that positive semidefinites would play a role in this. And one thing that's interesting is that if you have one slack matrix that is positive semidefinite, then every other slack matrix is either positive semidefinite, or you can permute things and possibly scale things such that it will become positive semidefinite. So I think this is more or less expected. And we can take a look again at the L1 cone. So these are the examples of slack matrices. And looking at the slack matrices, you can see that this can never be self-dual, because no matter how we exchange the rows, I can never remove the zeros from the diagonal. So yeah, you will not be able to get a positive semidefinite slack. But I should use this opportunity to mention an old result by Bark and Foran. They show that a 3-dimensional cone must have, a 3-dimensional self-dual cone must have an odd number of extreme rays. So this has 4 extreme rays, so it cannot be self-dual by this result. Very, very curious and interesting result. Now, one thing that I should mention is that the positive semidefinite slacks of a polyhedral cone, they are not only positive semidefinite, but they are also non-negative matrices. Why? Because the entries are inner products between extreme vectors, so they are all non-negative. So a natural question then is to understand how are the PSD slacks of self-dual cones related to W non-negative matrices. And here maybe I'll make a quick review of some of these things. So just for the sake of preciseness, I say that X is a W non-negative matrix if it's symmetric, positive semidefinite, and non-negative. And closely related to the W non-negative matrices, I have the set of completely positive matrices. So these are the matrices for which you can find some non-negative factorization of this form. VV transpose with V, a non-negative matrix. And these things are important because certain combinatorial problems can be solved using the completely positive cone, but this is a very computationally hard cone. So what people typically do is that they relax the completely positive cone to DNN. And in fact, for n greater or equal, sorry, n less or equal than 4, these two coincide, but they are different. Now, one thing I'd like to mention is that even to this day, there are many things we don't know about the facial structure of both the completely positive cone and the W non-negative cone. And typically, it's not easy to find X that's in DNN, but not in the completely positive cone. Now, to explain the next result, I need to go through one preliminary, which is the notion of irreducible cones. So I say that a cone is irreducible if it's not the sum of two non-trivial cones such that they intersect only at 0. So for example, Rn plus is not irreducible for n greater or equal to 2 because it's just a bunch of extreme rays. It's just the direct sum of extreme rays. And Sn plus is irreducible, the cone of positive indefinite matrices. Now, one thing that is nice is that for self-dual polyhedral cones, you can check irreducibility by looking at the support graph of a positive semidefinite slack. So if K is self-dual, it will have a positive semidefinite slack, and I can look at the support graph, which is just the graph where the vertices are numbered from 1 to n, and you have an edge if Mij is different than 0. And it turns out that K is irreducible if and only if the support graph is connected. Now that will be the somewhat curious / surprising result that we found, is that if you have a positive semidefinite slack of a self-dual irreducible cone, then M is not only a W non-negative matrix, but is an extreme ray of the W non-negative matrices. And in particular, if you have an extreme ray of the W non-negative matrices with rank greater than 1, this must be a matrix that is not in the completely positive cone. Because, well, all the extreme rays of the completely positive cone have rank 1. So the story is that if you pick a if you pick a positive semidefinite slack of a self-dual irreducible polyhedral cone, this will give you a DNN matrix that is not completely positive. Now, I'd like to look again at the cone over a pentagon. So just to remind, I pick a pentagon in the 2D space. I lift it to the 3D space, conify it, and build its slack matrix. Now, this is a PSD slack, And if I pick the support graph, this is a 5 cycle. So K is irreducible. So M generates an extreme ray of DNN5 that's not completely positive. So I look a bit in the literature, and these matrices, they have a technical name. So these are called extremely bad matrices. And so this name appears in this paper by Bureau and Streicher and Miriam Du. And I think they call this bad because it's exactly the BAD. Yeah, I don't know the story of this, but I suspect this might have played some role where they explicitly discuss the difference between the 5x5 DNN matrices and the completely positive matrices. And what, in fact, you can show is that you can characterize the extreme rays of the 5x5 W non-negative cone as either being rank 1 or being slack matrices of some irreducible cone over a pentagon. So you have this geometric characterization of extreme rays via slacks of self-dual, via slacks of pentagons. And this sort of gives a complement to some old results on DNN matrices given in this paper. Now, how am I doing with time? Okay. Are there any questions so far? If not, let me continue a bit. Now, there is another class of cones. This was introduced a bit more recently by Monique Laurent and Teresa Piovesan. These are the so-called completely positive semi-definite matrices. So the connection to completely positive matrices is this. So a completely positive matrix is one for which you can find a non-negative V such that X is equal to VV transpose. So it has a non-negative factorization this way. Now, a completely positive matrix, completely positive semi-definite matrix is one for which instead of having vectors that would correspond to the rows or the columns of V, you pick positive semi-definite matrix, and you get that the components of your matrix must be these inner products. So this gives rise to what's called the completely positive semi-definite matrices. And this contains the set of completely positive matrices. And this cone is even harder to analyze than the completely positive cone. Now, I think this is the weirdest result we got in this research, which is that if you pick a slack of a self-dual polyhedral cone, if S is not a diagonal matrix, then this is not going to be a completely positive semi-definite matrix. So yes, so this is quite unexpected. And the significance of having a diagonal slack is that a matrix has a diagonal slack if and only if it's simplicial, if and only if it's linear isomorphic to some non-negative orthant. And the informal conclusion is that positive semi-definite slacks of self-dual cones will typically neither be completely positive nor completely positive semi-definite. Now, I want to just give a bit of intuition or what is the proof strategy. It's more or less like this. So I start with a polyhedral self-dual cone, and I pick a PSD slack. And I suppose that it is completely positive semi-definite. So I can find a bunch of positive semi-definite AIs such that this holds. Now, what will happen is that if I pick the span of those, this will give an slice of the positive semi-definite cone that will be isomorphic to your cone. Now, what will be special is because the original cone was self-dual, this slice is going to be self-dual with respect to its span. Now, there is something called orthogonally projectionally exposed cones. So, Professor Henry invented this stuff, so Wittenberg talk about this in front of me. But so a cone is orthogonally projectionally exposed if every face is an orthogonal projection of it. So, for example, this is what happened with the pause semidefinite matrices. Every face of the pause semidefinite matrix is an orthogonal projection of the whole cone. So what will happen is that because this KL is self-dual on its span, the fact that the cone of pause semidefinite matrices is orthogonally projectionally exposed will imply that this slice is also OP exposed. Now, there is an old result by Sam and Bit-Shum-Tam that they prove that if a polyhedral cone that is OP exposed must be simplicial. And invoking this result from this very underappreciated paper, you can prove that this cone must be in the end isomorphic to Rn plus. Yes. So I'm moving to the final part of my talk. Are there any questions so far? Yeah, so the kind of self-duality that we've discussed so far, it's kind of a geometric self-duality. But in the study of polytopes and polyhedral cones, they consider other kinds of self-duality. So, for example, there is this notion of combinatorial self-duality, which just means that the cone, and it translates into our language, it just means that the cone and its dual are combinatorially equivalent. You can find some bijection between the faces that preserves the inclusion. Now, there are lists of these things. So there are people who work on trying to enumerate these things. So what we try to do is to check to which extent some of these combinatorial notions of self-duality imply geometric self-duality in our sense. And it turns out that you can answer part of these questions with semi-definite programming. And the idea is that, well, cones that are combinatorial self-dual are candidates for self-duality. So I pick, and looking in the literature, you can find the graphs that describe some of these polytopes. And you can get a support a matrix that describes the support matrix of potential slack matrices. For example, for the cone over the pentagon, that will be the support. And the idea would be then, the first thing, we try to permute this matrix so that it becomes symmetric and has no zeros in the diagonal. And if you cannot do that, it's because your cone cannot possibly be self-dual. And after that, we just try to find a DNN matrix that has rank D and whose support coincides with the support of your matrix. And then we factorize this matrix, and this will give a representation of your cone. It will give a geometric representation of your cone that is self-dual. For example, in the case of the pentagon, it would be the problem of completing these entries such that X has rank 3 and is doubly non-negative. Now, we pick up the simplest possible SDP that somehow tries to achieve that, which is just trying to maximize the sum of the entries, is subject to the diagonal entries being 1 and having the support that is specified. And we didn't care about the rank constraints nor anything. And it turns out that this works okay. So we were able to find the representation of many geometric self-dual representation of many cones. And there is this notion, I won't explain the details, of a cone being strongly involutive, combinatorially self-dual. And so these were considered in this paper here. And it turns out that all those cones seem to have numerically, they seem to have self-dual representations in our sense. And we are able to give this conjecture that these are in fact combinator equivalent to self-dual cones in our sense. So here's an example. So this is an example of a self-dual cone in R4 with 10 extreme rays. I mean, this is a slice. So the cone is 4-dimensional, so we pick a slice. And this is something that was computed numerically via this example. And this is more or less the story. If you have K, a self-dual, polyhedral self-dual cone, then K has a post-semidefinite slug. And this is if and only if. If K has a post-semidefinite slug, then it must be a polyhedral self-dual cone. And irreducible self-dual cones, they correspond, their positive semidefinite slugs corresponds to extreme rays of the NN matrices. And typically, PSD slugs of things that are not isomorphic to non-negative orthants are neither completely positive nor completely post-semidefinite. And in some cases, we can find self-dual cones via semidefinite programming. I guess, yes. Yeah, I think that's all I had to say today. Thank you very much.
Thanks a lot for the talk. Yeah, this is question and answer period. Please wait until I pass you the mic so we get the question recorded. Okay, are there any questions?
So you had the characterization of the matrix times the cone, AK. But so if you go to a semidefinite cone or something like this, does that just mean linear transformation of the cone?
So, sorry, which part?
Well, your characterization had a positive semidefinite matrix A times K is equal to the dual, right?
Ah, yes. So in the case of, for example, if you look at this in space of matrices, instead of being A, it will be like a linear operator and under appropriating a product with self-adjoint with non-negative, positive eigenvalues.
So do you know anything about the Euclidean distance matrices, the cone of Euclidean distance matrices?
So if there are any connections...
Is there any inner product where that is self-dual? No, it's not?
I don't know. So, yeah, so...
There is a linear transformation to the SDP cone from the EDF. Does that help?
There is a linear. Okay. There is a linear transformation, but that's not an isomorphism, right?
It's 1-to-1 to a face of the SDP cone.
Okay. So this is isomorphic to a smaller PSD cone, right? Yes. Okay. So then it's self-dual. So because self-duality is preserved under linear isomorphism, and then you can use the linear isomorphism to build in a product. So the notion of self-duality, in this general sense, on the existence of a product that makes things self-dual, this is invariant on the isomorphism. So if I'm getting the story correctly, I think the answer should be yes, if it's isomorphic to a face of the post-semidefinite cone. Thank you. Oh, for a question.
Any other questions? Oh.
So when you're trying to identify whether the cone is self-dual or not, So you write down the slack matrix and then you work with the slack matrix. Is it somehow, in terms of just the amount of information that you need to determine that, do you need the entirety of the slack matrix, or are there only some important entries that are enough?
Yeah, that is a good question. I mean, if you want to prove that the cone is not self-dual, then, for example, if you cannot have a slack matrix that has positive entries in the diagonal, then it is already out, right? So I guess for deciding non-self-duality, there are many things you can try to look at pieces of the, but to decide self-duality itself, I'm not sure. That's a good question, though.
Thanks.
Are there any other questions? If no, let us sing the speak again.